Unit 5, Stoich Point Review. You can access this review and this video at srhschem.wikispaces.com or on YouTube channel LEFFELlabs. The first section of the review is about stoichiometry. The first question gives us the Haber process and asks us a few stoichiometric questions about the balanced equation. First, how many moles of nitrogen are needed to make 24 moles of ammonia in H3? So my wanted quantity is highlighted in red, that's the moles of nitrogen, and I'm given 24 moles of ammonia. So we'll start with 24 moles of ammonia on top with 1 on bottom. And because this is already in moles, I can go straight to a mole ratio. So in order to cancel out, I need to have moles of ammonia on bottom. And I want to change moles of ammonia into moles of nitrogen. So at this point, once I solve this, I will have my answer in moles of nitrogen. So all I have to do is fill in my mole ratio. There is 1 mole of nitrogen for every 2 moles of ammonia. So that gives me 12 moles of nitrogen that can be that are needed in order to make those 24 moles of ammonia. The next question, I'm given 30 grams of nitrogen, and I want to know how many grams of ammonia can be made. So this is going to be similar to last problem, except instead of starting with moles, we're going to start with grams. The other thing I want to point out here is that it says excess hydrogen. That simply means that I have enough hydrogen to use up all 30 grams of that nitrogen. So we'll start with 30 grams of nitrogen, our given, over 1. Anytime that you are given something that isn't in moles, your first step is to convert it into moles. So in order to cancel out grams, I need grams on bottom, and I want to convert that into moles. At this point, my answer is in moles of nitrogen. So now I can go into a mole ratio. I could put moles of nitrogen on bottom and moles of what I want, which is ammonia, on top. And then I can go ahead and convert my moles of ammonia into grams of ammonia. So we went from grams of nitrogen to moles of nitrogen to moles of ammonia, and now we're going to go from moles of ammonia to grams of ammonia. So the first conversion factor is for moles and grams of nitrogen. So anytime you see moles with grams, that is going to be the molar mass. The molar mass of nitrogen is 28 grams per mole. A single nitrogen atom weighs 14 grams per mole. So since this is N2, because it's diatomic, we double that 14 to get 28. Next, I have mole on top of mole, which is again a mole ratio. That comes from our balanced equation. So in our balanced equation, there are 2 moles of ammonia for every 1 mole of nitrogen. Last one is grams and moles again. So we're going to need to find the molar mass of ammonia. So nitrogen is 14 and hydrogen is 1. So if we add up 1 nitrogen and 3 hydrogens, we get 17 grams per mole as my molar mass. So we end up with 36.4 grams of ammonia that can be formed from those 30 grams of nitrogen. The next question is asking us about the limiting reactant, and I'm given 10 moles of nitrogen and 12 moles of hydrogen. So we have 2 givens, which means we need to do 2 calculations. So we'll start off with our 10 moles of nitrogen. So I'm already in moles, so I don't need to convert to moles. I'm already there. I can go to a mole ratio. So I want to convert moles of nitrogen into moles of ammonia. Now, anytime you have a limiting reactant problem, you just pick a product and see how much of that product you can get with each of your givens. In this case, there's only 1 product. The only product you can choose is ammonia. So that's why we're going from moles of nitrogen to moles of ammonia. So the mole ratio is 2 moles of ammonia for 1 mole of nitrogen from the balanced equation, which means that if I start with 10 moles of nitrogen, I get 20 moles of ammonia. Now we need to perform the exact same calculation, except we're going to start with our hydrogen. So because hydrogen is already in moles, there's no need to convert. I can go straight to a mole ratio. So I'm using the mole ratio of ammonia to hydrogen, which is 2 to 3. So again, we only have 1 product that we can choose, and that 1 product is ammonia. So with those 12 moles of hydrogen, I can only make 8 moles of ammonia. Whichever one of the two that makes less product is the one that is limiting. So we took those two givens that are in blue and we just did two calculations. How much of my product can I get with 10 moles of nitrogen? How much of my product can I get with 12 moles of hydrogen? And whichever one makes less is going to be my limiting reactant. So that's going to be my 12 moles of hydrogen. The next problem begins with an unbalanced equation. So first thing we need to do before we can do any stoichiometry is we have to balance this. So I like to do the inventory method. So I break this up into the individual ions that are present. So I've got potassium. I have hydroxide, which is a polyatomic ion. Because it appears on both sides as hydroxide, I'm going to just keep it together. We could break this apart into oxygen and hydrogen, but that would make it more difficult to balance. So because it appears the same on both sides, we can just go ahead and keep it. So same thing for sulfate, for SO4. I've got CuSO4 and K2SO4. So instead of breaking that up into sulfur and oxygen, because SO4 appears unchanged on each side of the equation, I'm just going to count that as one unit, one sulfate. So now that we have our inventory, we need to go ahead and count. So there's one potassium, one hydroxide, one copper, one sulfate. And I'm going to go to the other side, do the same thing. 2 potassiums, 2 hydroxides. So that hydroxide in parentheses with the 2 after it means I have 2 hydroxides. 1 copper and 1 sulfate. So right away it should be very obvious how we're going to need to balance this. I have 2 potassium and 2 hydroxide on the product side of the reaction, and only 1 of each on the reactant side. So if I put a 2 in front of the reactant KOH, that's going to change the number of potassium and the number of hydroxide to 2. So at this point, we've got the same of each thing on both sides of the arrow, which means that we're balanced. Now we can get down and do some stoichiometry. How many moles of KOH are needed to produce 12 moles of K2SO4? So I'm asking for my wanted quantity is moles of potassium hydroxide, and I'm given 12 moles of potassium sulfate. So we start with our given, which is 12 moles of potassium sulfate, and we're already in moles, so we can go straight to a mole ratio. So I'm going to put mole of K2SO4 on bottom to cancel out. And I can convert this to moles of my wanted quantity, which is KOH. So at this point, I'm done. My answer will be in moles of KOH, which is exactly what we want. So I've got mole on top of mole, which means mole ratio. And good thing that we just balanced that equation, because then we know that the mole ratio is 2 moles of potassium hydroxide to 1 mole of potassium sulfate. So whenever I solve, I get 24 moles of KOH. The next problem, how many moles of copper sulfate are needed to react completely with 4 moles of potassium hydroxide? So my given this time is my 4 moles of potassium hydroxide. I'm already in moles, so I don't need to do any conversion to get to moles. I can go straight to a mole ratio. So I'm going to want to put moles of KOH on bottom in order to cancel it out. Then the top of my mole ratio is going to be moles of my wanted quantity, which is CuSO4. So at this point, if we plugged in everything and we solved, my answer would be in moles of CuSO4. So we're done. We just got to fill in our mole ratio. So from our balanced equation, there is 2 moles of KOH for every 1 mole of CuSO4. So whenever I solve this, I get 2 moles of CuSO4 are needed to completely react with 4 moles of KOH. Now this problem was very simple. The one above it as well. If you just look at the reaction stoichiometry, it's usually pretty easy to figure out what the answer is. We know that the only thing that I need 2 moles of is KOH. So everything else is a 1-to-1 ratio except for KOH. Number 3, once again, starts out with another unbalanced equation. So we're going to go ahead and use our inventory method. I've got sodium, then hydroxide, hydrogen, and sulfate. Now it kind of looks like I don't have hydrogen and hydroxide on both sides, but we're going to do a trick in just a bit, and then you'll see very clearly that we have hydrogen and hydroxide. We're going to change the way that we have water written. So let's do our inventory. There's 1 sodium, 1 hydroxide, 2 hydrogens, 1 sulfate. 2 sodiums, and now we're at counting the hydroxide and the hydrogen, which it's not obvious that they're there. So we're going to take our water and we're just going to write it as HOH. That's the same thing as H2O, except whenever I write it this way, you see that it's 1 hydrogen and 1 hydroxide. So 1 of each. We also have 1 sulfate. So, good place to start. We can start with the sodium. So if I put a 2 in front of NaOH, that's going to give me 2 moles of sodium, but it also gives me 2 moles of hydroxide. So now I need to go to the other side of the equation and do something to the hydrogen and to the hydroxide so that I end up with 2 moles. So if I put a 2 in front of our water, our HOH, now we've got 2 moles of hydroxide and 2 moles of hydrogen. And everything's balanced, so now we can go ahead and do some reaction stoichiometry. The question asks, what is the limiting reactant if 20 grams of NaOH react with 22.5 grams of H2SO4? So once again, I have 2 givens, which are in blue, so that means that I'm going to have to do 2 calculations. And I just want to know what the limiting reactant is. I would also like to point out that the next question is asking for the theoretical yield in grams of sodium sulfate. So again, whenever we're doing these limiting reactant calculations, you just pick a product. Now I'm going to very intentionally choose sodium sulfate as my product because the next question asks me about sodium sulfate. I'm also going to take my calculation all the way to grams. We could, if we're just trying to figure out the limiting reactant, we could just stop at moles of a product and compare and then get our answer that way. But since the next question is asking me for how many grams of Na2SO4 I can make, I might as well do grams of Na2SO4 for both of my calculations. So again, we're just intentionally choosing this because it's going to help us solve the next problem. You could still solve for water if you picked that product instead, and you would still figure out the correct limiting reactant. But then once you got down to B, you'd have to do another calculation. So you'd have to take your limiting reactant and figure out how much Na2SO4 could be made from that. So let's start with our 20 grams of sodium hydroxide. So since sodium hydroxide is in grams, we need to convert it into moles. So grams of NaOH can go on bottom to cancel, and moles of NaOH can go on top. Once we're in moles of NaOH, we can then do a mole ratio in order to convert moles of NaOH into moles of Na2SO4. So mole of NaOH goes on bottom, and moles of sodium sulfate goes on top. Then we can go ahead and take the moles of sodium sulfate, put that on bottom to cancel, and just convert it into grams. So 2 of these conversion factors are just dealing with the fact that we weren't given moles and we're not asking for moles for our final answer. So first I've got grams and moles of sodium hydroxide, so that's the molar mass. So you add up the masses from the table of elements of sodium, oxygen, and hydrogen, and that gives us 40 grams per mole for the molar mass. Next, I've got mole on top of mole. So this is a mole ratio, which comes from the balanced equation. So in my balanced equation, there is 1 mole of sodium sulfate for every 2 moles of sodium hydroxide. So once we finish this step, my answer is now in moles of sodium sulfate. And since the next question asks for grams, we might as well just go ahead and use the molar mass to convert it into grams. So this gives me 35.5 grams of sodium sulfate. So now I need to repeat the same calculation, except this time I'm going to start with 22.5 grams of sulfuric acid instead of the sodium hydroxide. So for the first step, again, since I'm not given moles, I need to convert it into moles. That's going to be molar mass. So grams of H2SO4 goes on bottom to cancel. I'm converting it to moles of H2SO4. Now that I'm in units of moles, I can go ahead and use a mole ratio. So mole of H2SO4 will go on bottom, and mole of Na2SO4 will go up top. And then one more step, we'll just convert the moles, put that on bottom, into grams. So my first conversion factor is the molar mass of H2SO4. So you add up the mass for each of those elements, 2 hydrogens, 1 sulfur, and 4 oxygens, and we get a molar mass of 98.1 grams per mole for sulfuric acid. Next, I've got mole on top of mole. So that is a mole ratio, which comes from balanced equation. So there is 1 mole of sodium sulfate for every 1 mole of sulfuric acid. Last step is grams and moles, so that's the molar mass. So that's the same as above, it's just the molar mass of sodium sulfate. And I get 32.6 grams of sodium sulfate. So as far as which one is limiting, it's whichever one makes less product. So the most Na2SO4 that I can make is 32.6 grams. Then I'm going to run out of my limiting reactant, which is my 22.5 grams of H2SO4. So with these limiting reactant calculations, pick a product, see how much of that product you can make with your first given, and then see how much of it you can make with your second given, and whichever one makes less is your limiting reactant. And you can choose, if you're clever, if you're careful, you should read the next problem and see if it asks you for any specific quantity. So because the next problem asks for grams of Na2SO4, the product that I picked was Na2SO4 because I have to figure that out for the next one anyway. Why is it important to know the limiting reactant in a reaction? So the limiting reactant will determine how much product we can make by the reaction. This allows us to do things like find the actual yield, the percent yield, the theoretical yield. It also allows us to carefully choose our amount of reactants and products. Let's say that one of the reactants is very expensive. So I want to make sure that I use it all up. I would make sure that I had enough of my other reactant in order to use up all of that expensive reactant so I don't waste any. A student performed the reaction above and obtained 29.60 grams of sodium sulfate. What is the percent yield? So this is an equation that you should have memorized. Percent is always some part over the whole. So the actual yield is the part that you actually get, and the theoretical yield is based on calculations, how much you could get. So theoretical yield comes from calculations. My actual yield is what we actually get. So we just divide those two. It's the ratio of the actual over the theoretical times 100%. So our percent yield here is 82.6%. So maybe while this reaction was occurring, we spilled some of the product, or perhaps something happened and we just lost some of it, or maybe our initial reactants we didn't have as much as we thought we had. The next section is about solutions, and it focuses on solution calculations that you'll have to do. So number 4 says to calculate the molarity of a solution made with 150 grams of sodium chloride in 800 milliliters in water. So molarity is how we measure concentration in chemistry. It is the moles of solute per liters of solvent. So we have to take our 150 grams of NaCl and convert it to moles so that we can figure out the moles of solute, which is on top in our equation. So I start with 150 grams of NaCl, and I need to cancel out grams and convert it into moles. So this will give us moles of NaCl. My conversion factor has grams and moles, meaning it's the molar mass of sodium chloride. So we can calculate that from our table of elements, and we get 58.44 grams per 1 mole of sodium chloride. So we can solve, and we get 2.57 moles of NaCl. Next, I've got to convert my 800 milliliters into liters. So this is just a metric system conversion. The nice thing about the metric system is that everything is based on powers of 10. So I need to put milliliters on bottom, liters on top to cancel. Milli means 1,000 times smaller. So 1 liter is 1,000 milliliters. So 800 divided by 1,000 gives us 0.8 liters. Now we just plug it into our equation and solve for molarity. So I'm going to take 2.57 divided by 0.8, and I get 3.21 molarity. So you would say that this solution has a concentration of 3.21 molarity, or you would say it's a 3.21 molar solution of sodium chloride. Number 5 asks us how many moles of hydrochloric acid are present in a 10 milliliter sample of 6 molar hydrochloric acid. So first we need to remember our molarity equation, moles per liter. So I need to take my 10 milliliters, and my equation calls for liters, so I'm just going to convert. So that's a simple metric conversion. So milliliters goes on bottom to cancel out, and I want to change that into liters. Milli means 1,000 times smaller, so 10 milliliters is 0.01 liters if we divide by 1,000. Now I'm going to plug into the molarity equation, and this time I'm solving for moles of solute, which is in this case hydrochloric acid. So I need to get X by itself. I need to isolate that variable, so I need to get rid of that 0.01 on bottom. Right now, we're dividing by 0.01. So if I do the opposite operation, which is to multiply by 0.01 liters, that will cancel out, and it'll leave us with the number of moles is equal to 0.06 moles of hydrochloric acid. So it's very important to note that whenever we're talking about a solution, I know that it has liters in it, and we tend to think, oh, 22.4 liters is 1 mole. That's only for a gas. This is a solution. So I'm going to have to use my molarity equation to figure out the moles based on the molarity and the volume of solution that I have. Number 6 is about performing a dilution. So how many milliliters of 5 molar sodium hydroxide are needed to prepare 175 milliliters of 1.25 molar hydroxide? So I'm taking a high concentration of sodium hydroxide, and I want to dilute it down to a lower concentration, and I want 175 milliliters of that. So our equation is M1V1 equals M2V2 for a dilution. So M1 is our initial molarity, and V1 is the initial volume. So it doesn't really matter which one you pick is which, as long as they're paired correctly. So for example, the question mark milliliter goes with 5 molar, and the 175 milliliter goes with 1.25 molar. So at this point, we just plug it in. I need to isolate X to be by itself. So M1 is 5, V1 is X, that's what we're solving for. M2 is the new concentration, and V2 is the new volume. So I need to isolate X, divide both sides by the 5 molar. We see that the M's cancel, so the molarity cancels out, meaning the only unit left is going to be milliliters. So in this case, because it's given us 175 milliliters and it asks for milliliters, we don't need to do any conversions there, because whenever we plug everything into our equation, the molarity is going to cancel out and leave us with milliliters. So I get 43.75 milliliters of 5 molar NaOH. So if I take that and dissolve it up to a total volume of 175 milliliters, that's going to give me my 1.25 molarity of sodium hydroxide. The next section of questions is also about solutions, but this is focusing more on the concepts of solutions. So number 7, explain why sodium chloride will dissolve in water, but not in carbon tetrachloride in terms of polarity. So first, NaCl is an ionic compound. We've got sodium ion and chloride ion, a metal and a nonmetal, so we know that this is ionic. And there's our Lewis dot structure. So we get sodium with a positive charge and chloride with a negative charge. Water is polar. So water is a covalent compound, and if we look at the structure of water, like the Lewis diagram down at the bottom of the screen, if I cut that right in half, the two halves are different. Oxygen is also very highly electronegative compared to hydrogen. So this difference on the two sides of this water molecule are going to cause it to be polar. If we look at carbon tetrachloride, this molecule is very symmetric, and symmetric means nonpolar. Also, the difference in electronegativity between chloride and carbon may be large, but the fact that there's 4 of these chlorides, they're all pulling those electrons in opposite directions, so it all cancels out. So carbon tetrachloride is nonpolar. So like dissolves like is a phrase that will help you to remember that a solute with a charge, so this could be something that is polar or something that is ionic, can only be dissolved in a polar solvent. So something with a charge can only dissolve something else with a charge. Nonpolar will only dissolve nonpolar. So since salt is ionic, it can dissolve in water because water is polar. But the carbon tetrachloride is nonpolar, so their polarities are different, meaning that they won't dissolve the salt in the carbon tetrachloride. Next one is NaCl an electrolyte. Explain why or why not. So this has got 2 pieces to it. So first, in order to conduct electricity, I gotta have charges such as ions, and those charges must be able to move. So the way that happens is by dissolving in water. So number 1, it has to be soluble in water, and number 2, it has to form ions when added to water. Now, ionic compounds, ionic solids, are pretty much all water soluble. So if we look at our solubility rules, we can confirm to make sure that NaCl is going to be water soluble. It says that group 1 ions are always soluble. So NaCl, check, it is water soluble, and double check, it forms ions, Na plus and Cl minus, when added to water. So this is definitely an electrolyte. Number 9 is asking us to summarize the properties of solution, suspension, and colloid. So a solution, colloid, and suspension, these are all mixtures. The difference is that the solution is a homogeneous mixture, whereas colloids and suspensions are heterogeneous mixture. The best way to understand this is to relate the size of the particle to the different properties. So an example of a solution, you can think of salt water. The particles inside of a solution are very, very small. They're individual ions or atoms. So in the case of salt water, whenever that dissolves, I get a sodium ion and a chloride ion. Very small individual particles. So you can think of that as being like the size comparatively of a marble. Next is a colloid, and an example of a colloid would be milk, fog, and air. These are examples of colloids. So these particles are going to be a little bit bigger. So think of like molecules like sugars present in milk or fat molecules present in milk. So comparatively, these particles are a little bit bigger. You can think of them as being like the size of a softball. A suspension would be like muddy water. So these particles are very large. They're aggregates of many molecules stuck together. So you can think of them comparatively as being the size of a basketball. So for all of these properties, the settling, the filtering, the scattering of light, we need to think of them in terms of the relative size of the particles. So in the case of a solution, there's no settling. This is because these particles are so small that the solvent, the water usually, can just hold those particles up, preventing them from settling down to the bottom. Same thing with colloid. Those particles are small enough that the solvent holds them up. Now, in the case of a suspension, because we have these big, large, heavy particles, these are going to fall to the bottom of whatever container they're in and settle out on the bottom. Next is filtering through filter paper and filtering through a membrane. So the key thing here is to remember the relative size of the particles and the size of the holes in the filter paper. So filter paper has big holes. So if the holes are really big, small particles like salt water and the small particles like in milk, those are going to be able to pass through because they're smaller than the holes in the filter paper. So if I were to filter salt water, at the end I would still have salt water. And if I were to filter milk, at the end I would still have milk. It would all pass through the filter paper. But if I were to filter muddy water, all of the mud and the dirt, which are large particles, would get caught in the filter. They're too large to pass through those holes. So my muddy water would come out clear because we'd catch all of the mud. For a fine membrane, the important thing to remember is that those holes are a little bit smaller. So my solution is still going to pass through because those particles are very small. But my colloid and my suspension, those particles are big enough that they get caught. They're too large to pass through the small holes of the membrane. So if I pass my salt water through a membrane, it's still going to be salt water on the other side because the sodium and chloride ions are small enough to pass through. My milk and my muddy water, however, I would catch all those particles. So my milk would come out as clear water because I would catch everything else. Same thing for my muddy water. It would come out clear because we caught all of the mud. Last is the scattering of light, which is also known as the Tyndall effect. The Tyndall effect is the scattering of light by particles. So you can think of the particles as being little mirrors. And the bigger the mirror is, the more light that it can scatter. So in the case of our salt water in our solution, those particles are so tiny that we can't see the light that they're scattering. It's just too little, we can't see it, so it doesn't scatter light. In the case of a colloid or a suspension, since those particles are bigger, they're able to scatter light. So the good example of this would be to take like a laser and shine it through a solution, a colloid, and a suspension. If we shine it through a solution, we can't see the path of the beam. We can maybe see the beam, hitting the other side of the container, but we're not going to be able to see it actually through the solution. In the case of a colloid or a suspension, we'll be able to trace the line that laser is making as it travels from one end of the beaker to the other end of the beaker inside of our liquid. So that would be the Tyndall effect. Number 10 are questions about solubility curves. So we got to be able to read our solubility curve graph here. So the way that this was done is we took 100 grams of water at different temperatures and we saw how much of each solute could dissolve in that amount of water at each temperature. We repeated this for a whole bunch of solutes. So there's a whole bunch on there, and rather than giving us an individual graph for each of these lines, we just put them all on one graph. So it is a little tricky. You want to make sure that you're looking at the right line. So it's always a good idea to have a highlighter or something like that so you can trace the line and make sure you're reading the correct numbers. First question is, why does sulfur dioxide, ammonia, and hydrochloric acid show negative slopes? So if you look at those three, the thing they all have in common is that they're gases. Gases become less soluble as the temperature of the solute, as a solvent, increases. So as the water gets warmer, we see that the gas is less soluble. So the solubility goes down as temperature goes up. For most solids, as temperature goes up, solubility goes up. There are a couple of exceptions, so you're just looking for anything that's a solid line that is decreasing. So like sodium sulfate is a little bit weird. It's a solid, but it becomes less soluble as temperature goes up. But again, that's all just related from being able to read the graph. So how much sodium chloride can dissolve in 200 grams of water at 90 degrees Celsius? So the key thing there is that it's asking about 200 grams. The chart is only for 100 grams. So if we find our sodium chloride line, if I have 100 grams of water at 90 degrees Celsius, I can dissolve 49 grams of sodium chloride in that amount of water. If I double the amount of water, that means I'm going to double the amount of salt that I can dissolve in it. So in 200 grams of water at 90 degrees Celsius, 98 grams of sodium chloride can be dissolved. A saturated solution of potassium chloride is made at 80 degrees Celsius. If the solution cools to 10 degrees Celsius, how much solid KCl will precipitate? So first, let's find our line for KCl. And at 80 degrees, I can dissolve 52 grams of potassium chloride. But at 10 degrees, I can only dissolve 30. So if I saturate my solution at 80 degrees, it's got 52 grams of potassium chloride. But if I drop that down to 10 degrees, the difference, which is 22 grams, is what's going to fall out. So we just did 52 minus 30, and that's the difference that can't be dissolved. That's what's going to fall out as a precipitate, as a solid.